So this is the third video of the series of 3 investigating trigonometric identities with complex numbers. In the first one we dealt with cos theta equals various a's and ai combinations, and in the second one we dealt with sine theta equals various ai combinations, and in this third one we are, amongst other things, going to answer this question here. I strongly recommend that you do watch those first 2 videos. The links are in the description to this video. Amongst other things, in those videos we did find and prove that if cos theta equals a, where a is greater than 1 and a is contained in the reals, then theta is equal to minus I log a minus root a squared minus 1, and likewise if sine theta equals ai, then theta equals minus I log minus a add root a squared add 1, and we'll be using these 2 identities a little bit later, and we will be answering this question a little bit later as well. But first of all, trigonometric identities with complex numbers, it's very simple, is that if they work with real numbers, they work with complex numbers, so there's nothing further to learn. So let's just do a couple of proofs of that. For example, let's have a look at cos squared theta add sine squared theta equals 1, which we know is true for reals. Okay, well, how do we prove that for complex numbers? Well, just reminding ourselves that e to the I theta is equal to cos theta add I sine theta, and e to the minus I theta is equal to cos theta minus I sine theta. There's at least 2 ways of proving this. The first way is we could simply go cos theta add I sine theta times cos theta minus I sine theta, which equals e to the I theta times e to the minus I theta, which by the power rules equals 1. Expanding this out here, we get cos squared theta add I sine theta cos theta minus I sine theta cos theta minus I squared sine squared theta, and as I squared is minus 1, that gives us cos squared theta add sine squared theta equals 1 for complex numbers. That's one way of proving it. There is another way, is what we could do is we could use the identities that we've been using in the first 2 videos. Cos theta is e to the I theta add e to the minus I theta over 2, and sine theta is equal to e to the I theta minus e to the minus I theta over 2i, and then we could say, okay, well, cos squared theta add sine squared theta, and we just basically expand all those, is going to be equal to a quarter e to the 2i theta add 2 add e to the minus 2i theta minus, because when we square sine theta, that I becomes minus, that becomes minus e to the 2i theta minus 2 add e to the minus 2i theta, and basically everything cancels out, leaving us with 2 plus 2 is 4, which is 4 over 4, which equals 1. So they are 2 ways that we can prove that cos squared theta and sine squared theta is also true for complex numbers. Let's just do another couple. We'll do cos 2 theta and sine 2 theta. Well, we know that cos 2 theta is cos squared theta minus sine squared theta in the real world, and we know that sine 2 theta is 2 sine theta cos theta in the real world. How can we prove in the complex world that's also true? Well, again, e to the I theta equals cos theta add I sine theta, so e to the 2i theta is equal to cos of 2 theta add I sine of 2 theta, which equals e to the I theta times e to the I theta, which equals cos theta add I sine theta times cos theta add I sine theta. Expanding that gives us cos squared theta add 2i sine theta cos theta minus sine squared theta, and then all we have to do here and here is compare the reals, which gives us cos 2 theta equals cos squared theta minus sine squared theta, and then compare the imaginaries, which is sine 2 theta equals 2 sine theta cos theta. So it works, and that's basically, you know, there are 3 examples, but we could carry on proving any trigonometry identities that we wanted. Now let's go back to this question here and solve that using these 2 identities that we have proved in previous 2 videos. Okay, so let's let cos theta equal 3. Then we know that as cos squared theta add sine squared theta equals 1, we know therefore that sine squared theta equals 1 minus 9, which equals minus 8, i.e. sine theta is equal to 2 root 2 I. So what we can do now is we can stick in this value 3 into the formula for cos theta, and we can stick in this value here for the sine theta, and we get that theta equals minus I log 3 minus root 3 squared minus 1, which equals minus I log 3 minus 2 root 2. And when we stick the sine theta into our sine theta form, all I'm doing is I'm putting them into these 2 formulae here, which we've already established in the previous 2 videos. So therefore theta equals, where are we? Minus I log, this is putting it into the sine this time, minus 2 root 2 add root 2 root 2 squared add 1, which equals minus I log 2 root 2 squared add 1, the square root of that is 3, minus 2 root 2, and again, that equals the same thing, which it must be. So basically what we've said is if cos theta equals 3, then theta, by our formula above, is minus I log 3 minus 2 root 2, and as sine theta is 2 root 2i, which it must be because cos squared plus sine squared is 1, and we stick that into our sine formula, we get the same theta, which we must do, which is minus I log 3 minus 2 root 2. Let's just continue this, because we get some quite wacky answers here. So we know that cos theta is 3, and we know that sine theta is 2 root 2 I. All right, what's sine 2 theta? Well, sine 2 theta is 2 sine theta cos theta, which we know, cos theta. Well, that therefore is going to be 2 times 2 root 2 I times 3, which is 12 root 2i. So sine of 2 theta is 12 root 2i. Well, cos of 2 theta is cos squared minus sine squared. So that equals cos squared is 9 minus sine squared. We've got to be careful here. 2 root 2i squared is plus 8, which equals 17. So therefore, if cos theta is 3 and sine theta is 2 root 2i, i.e. theta is minus I log 3 minus 2 root 2, then sine 2 theta is 12 root 2i, and cos 2 theta is 17. We're getting some very wacky results. But of course, sine squared 2 theta add cos squared 2 theta must equal 1. So let's just check. Well, that equals 12 root 2i squared add 17 squared, which is, well, 12 root 2 is minus 288 by the time we squared the I, add 289, which equals 1. So it all works. So far, so good. Now finally, this is quite cool. So we know that cos 2 theta is equal to 17 if cos theta equals 3. Well, let's just put this cos 2 theta here into our formula at the top of this video, and we get that 2 theta equals minus I log 17, because that's the A in the formula at the beginning of this video, 17 minus the square root of 17 squared minus 1, which equals minus I log 17 minus root 288, which equals minus I log 17 minus 12 root 2. So, we'll have to go on another page now. So we know that theta, where are we? Theta is minus I log 3 minus 2 root 2, and we've just shown that 2 theta is minus I log 17 minus 12 root 2. We've got to think, hang on a sec, is that correct? So let's have a look. Well, if we look at 3 minus 2 root 2 squared, that comes to 9 minus 12 root 2 add 8, which equals 17 minus 12 root 2. So therefore, we can rewrite this as 2 theta equals minus I log 3 minus 2 root 2 squared, and therefore that equals minus 2I log 3 minus 2 root 2, And we can see that so 2 theta is minus 2I log 3 minus 2 root 2, which, as it must be the case, it is twice as large as theta, which is minus I log 3 minus 2 root 2 here. So it all works. So we have no problems with using complex numbers with the trigonometric identities, and in actual fact we could have answered this thing here by inspection now that we know that, because cos squared of anything add sine squared of anything, doesn't matter what it is, complex or real, equals 1. Well, I hope you found this interesting. If you have, please press the little thumbs up button and subscribe to the Gresty Academy YouTube channel. Thank you.